Welcome back. We are continuing our lectures on this notion of extended formulations. And as we introduced in the previous lecture, the central question is, given a polytope, can we find a polytope in potentially higher dimensions that has only a small number, a polynomial number of facets, and that projects down, or as an affine transformation, gives exactly our original polytope in lower dimensions. And in the previous lecture, we saw that a polytope which requires exponentially many facets to describe, namely the permutahedron, is in n dimensions, is really just the affine transformation, in particular just the projection onto the first n dimensions of an order n squared, specifically a n squared plus n dimensional polytope that has n squared plus 3n inequalities that describe it. So that was a positive example where this can be done. But now we're going to define this question a little bit more formally and see where that takes us. So I want to define this notion of extension complexity, which is very natural given what we've seen so far. It's just going to be the extension complexity of a polytope is going to be the minimum number of inequalities needed to describe a polytope whose affine projection is a desired polytope. So let me write that down. The extension complexity, or extended formulation complexity, I'll use both of those interchangeably, of a polytope P is the minimum number of inequalities needed to describe a polytope Q such that P is an affine map of Q. So this is the extension complexity. And a few notes that we're going to talk about more. We're just talking about inequalities. So again, the canonical way to think about this is that if P is the polytope AX less than B, then we're looking for a polytope Q that has more dimensions, XY. Let me write it to exactly match the notation here. So P is all X such that AX less than B, and Q is all pairs XY such that CX plus DY is less than D, such that X is in P if and only if there exists Y such that XY is in Q. So this is the concise translation of what the definition is saying. And the number of rows of the matrix CD is the extension complexity, or the minimum number of rows over all such Q is the extension complexity. And as we mentioned in the previous lecture, we can easily solve this extension. Extended formulations are compatible with solving linear programs. That means we can solve a linear program over Q. And as I mentioned, if we can use Q to optimize, to find separation for P, etc. So if we have such a Q in hand, that essentially means, given all the machinery that we have developed, ellipsoid algorithm and so on, that we can solve a linear program over P efficiently. So let me write some of these points down here. So first of all, by the ellipsoid algorithm, and equivalence of separation and optimization we know that a problem, a linear optimization problem, is efficiently solvable if and only if there exists a polynomial time separation oracle. Okay, so this statement has nothing yet to do with extension complexity. A linear program is efficiently solvable if and only if there exists a polytime, or an efficient, I should be using the same words here, separation oracle, or separation algorithm. So we know that separation in this sense and optimization are equivalent, and we know that this is a characterization of easy and hard problems, linear programs. Now, what about bringing this back to extension complexity? If a particular polytope P has a polynomial size extension, in other words, if its extension complexity is polynomial, then the optimization problem is efficiently solvable. And conversely, if the optimization problem over P is not solvable efficiently, then P obviously cannot have a polynomial size extension complexity. This is just a contrapositive of the statement. Cannot have a polynomial extension complexity. Now let's think about what this doesn't say, or rather, so what happens if P is a problem where unless P equals NP, we believe that solving a linear program over P is hard. We've discussed examples like that. Max cut is such an example. Then immediately these 2 points here tell us that P cannot have a polynomial size extension complexity. So if P is again the polytope, the cut polytope, we know that we already know before we do anything that there's no way that it has a polynomial time extension complexity as long as we believe that P does not equal NP. So in this sequence of lectures, we're going to show that a particular polytope, actually very related to the cut polytope, called the correlation polytope, we're going to see this in subsequent lectures, has a exponential extension complexity. In other words, there does not exist an extended formulation of polynomial size. Now, by itself, this result is not at all surprising, again, because we believe that P does not equal NP, and therefore we already know that there couldn't exist an extended formulation that's polynomial size. So that's not the point of these lectures. The point of these lectures is going to be to develop the machinery to show these lower bounds. So this is going to be the story of this and the next lectures in this series. Now that said, it's important to note that unlike this equivalence between separation and optimization, which we have thanks to the ellipsoid algorithm, there is not an if and only if statement between a problem being polynomially solvable and having a small extension complexity. And this was finally decisively demonstrated on a problem that we're very familiar with because we've worked on for so long. And this was, so let me write it this way. So however, the above statement about P having a polynomial size extension, then the optimization problem is solvable. The above statement is not an if and only if. In other words, if P does not have a polynomial size extension, that doesn't by itself imply that the problem is hard. And this is a theorem due to Thomas Rothfuss in 2017, so pretty recently, that says that the extension complexity of the perfect matching polytope for the complete graph is exponential. And well, we know because we gave in detail the algorithm in previous lectures that we can solve an LP over this polytope in polynomial time. Okay, so this is essentially the agenda of the next several lectures, and we're going to develop some nice machinery for polytopes and connections to a concept called non-negative rank. And then subsequently, we're going to also develop the connection to communication complexity. So we will get to all of those. So first, let's talk about non-negative rank. Suppose P is a polytope that's given as a convex hull of vertices, x1 to xv. Now, I don't care if v is, we're not talking about, this list doesn't have to be small. V could be exponential size. For most problems that are of interest to us, that indeed will be the case. We have exponentially many vertices. And this has some representation in terms of inequalities. Again, by writing this, I'm not in any way implying that A has a polynomial number of rows. Again, for all problems, if it has a polynomial number of rows, then this is already shows that our problem has polynomial number of facets. We don't need to look for any extensions. So we should think about both V and M, where M is the number of rows. For now, both V and M are going to potentially be exponential in size. And now I'm going to define an exponential size matrix. S is the slack matrix, where its entries are going to be indexed by extreme point, comma, inequality. So its entry ij is, let me write down what it is. It's bi minus minus ai times xj, where ai transpose is the ith row of A, and xj is the jth vertex of P, as given in this list. Okay, again, we're not talking about any. This is exponential size to write down. We're not writing this down. We're just defining what it is. So this is a matrix that has all non-negative entries because every entry in xj, every extreme point, of course, is feasible for every constraint, and therefore the slack is going to be greater than or equal to 0. And when is Sij equal to 0? Sij is equal to 0 if the vertex xj lies on the face described by that inequality. It lies on that facet defined by ai transpose x is equal to bi. So that's a facet of our polytope, and the slack matrix is 0 for every entry j of Sij where those extreme points lie on that on that facet. So a theorem that's due to Yannakakis, dating from 1991, says that this slack matrix exactly characterizes the extension complexity in the following way. The extension complexity, in other words, the minimum complexity, meaning number of inequalities, of an extended formulation for the polytope P is exactly equal to this concept called the non-negative rank. The non-negative rank of the slack matrix S, which I'm going to denote as rank plus of S, or sometimes rank plus of S when I'm feeling like I need to save writing two letters. So let me define now what is the non-negative rank. Given a matrix M, not necessarily square, where M is component-wise non-negative, so it has non-negative entries, the rank plus of M, non-negative rank, is the minimum integer R such that M is equal to U V transpose, where U and V have the appropriate dimensions. So if M is, let's say it's M by, well, I'll use M by V since this is what we have in our example above. Is an M by V matrix, then that means that U has to be M by R, and it has to be non-negative. And V is going to be V by R, non-negative. So again, pictorially, this means that that M is equal to U times V transpose, and the small dimension is R. So let me give you a little example. So let's look at this matrix: 1 1 0 0 0 1 1 0. I'm just rotating this. 0 0 1 1 1 0 0 1. And so this is a 4 by 4 matrix. As you can see, if I sum all of its rows or all of its columns, there's exactly 2 rows in every row and column, and that shows us that it can have that its rank is equal to 3. So let's call this M. So certainly the rank of M is equal to 3, but with some work you can check that its non-negative rank is actually 4. Now, its non-negative rank can be at most 4, since the matrix itself is a 4 by 4. But this is a simple example that shows that the non-negative rank is different, can be different than the rank. Okay, so back to Yannakakis' theorem. It says that you look at the slack matrix, and it's a matrix that is M by V, exponential size. Whatever its non-negative rank is, that is exactly equal to the extension complexity. And we're going to show this, we're going to prove this by showing both directions. So we're going to show that if we have any non-negative factorization of S, we can build an extended formulation. And therefore, the size of an extended formulation is not going to be any bigger than the size of any such factorization. And in particular, it's going to be no bigger than the non-negative rank. And then in the other direction, we're going to show that if we have an extended formulation with R inequalities, then we can use that to create a non-negative factorization of S whose small dimension is R. And that shows the other inequality, that namely that the non-negative rank is no bigger than the size of the extension complexity. It's no bigger than the size of any extended formulation. Okay, so let's show these both of these directions. Okay, so we have our matrix S. This is our slack matrix. So again, just writing from the previous, Sij is equal to Bi minus Aixj, where xj is a vertex and I is, whoops, I wrote Ai. I mean Ai, where Ai transpose is the row, the ith row of A. Let's let R in this direction equal to the non-negative rank of S. And that means that, in particular, that means that I can write S, just as in the previous slide, just as in the definition, S is equal to UV transpose, where U is an element of R. M by R, and V is an element of R. Whoops, these are non-negative, of course. And V is an element of V by R. So the claim is that U actually gives us our extended formulation. So let's look at the polytope Q. That's all pairs XY in Rn plus R, such that AX plus UY equals B, and Y is non-negative. Something to note here is that this, you may wonder, why does this, suppose we were able to show, that the projection of Q onto the first n coordinates indeed gives us P. You may be concerned and say, wait a second, you've not only used R inequalities here, but you've also used an exponential number of equalities, because here is that same A. Now we have a huge number of equalities. But let me remind you that the point here is that extension complexity is the number of inequalities. Because if you are given this system that I just wrote down, if you're given this description of Q and you have unlimited computational power, then what can you do? What are we guaranteed? This is so here we have M, which is a huge number, equalities in n plus R variables, and we know, because this is non-empty, because Q is non-empty, that these have to have a huge number of redundancies. We obviously can't have more than n plus R independent inequalities in n plus R dimensions. If we had n plus R, then that would mean that Q is just a single point. So that means that in general, they're going to be fewer than n plus R equalities that are non-redundant. And whenever you have an equality, I can just use that to eliminate a variable. Okay? So again, all of this can be done with potentially exponential effort to find it, but we know that it must be so, and therefore, if what this is saying is that if such a Q exists and is indeed its projection gives P, then we could use that potentially, again with exponential effort. We don't care about that. We could use that to produce another Q that doesn't have all of these exponentially many equalities, that again gives a projection of Q, projection onto P. Okay, so that's the key point here, that if we can show that the projection of Q is equal to P, then we've succeeded in showing that the extension complexity of P is no more than R, which is the number of inequalities. because y is a vector in R, little r. Okay, so let's show this. So basically, what we're claiming, what I mentioned, is that this is an extension. This is an extended formulation of P. So first of all, I need to show that for any element of P, there exists a y so that xy is in Q. And I'm just going to do that for all of the extreme points. And that will certainly be enough since Q is convex. So we'll show this again in two parts. First, we show that for any xj, this is an extreme point, j equals 1 to v, an extreme point or vertex of P, there exists a yj such that yj is non-negative and axj plus uyj equals b. And you can almost see what's going to happen. Here. We've got our axj minus b. That's all the slacks. And in order to make that equality, we just need to make uyj equal to that jth column of the slack matrix. So let's write down the details. We simply do this by, let's let yj. And what are the dimensions of yj? Yj is in an r-dimensional vector. So what is yj pictorially going to be? It's going to be one of the columns of V transpose. In other words, a row of V. So let yj, which is an R, be the jth row of V. In other words, the jth column of V transpose. And remember that, again, S, I think that picture is helpful from the previous slide. This is V transpose, this is U, and so this is Y. So let's check. So let's take any row of this matrix. So we've got AI xj plus ui, the ith row, times yj, which is vj, and just by definition, this is equal to bi minus sij plus sij. In other words, aixj is just bi minus whatever the slack is by definition, and uivj is sij, so this is bi. And also note that because we have a non-negative factorization, yj is greater than or equal to 0, which is exactly what we need. So we've shown that every single one of the extreme points of P, and therefore all of P, is contained in the projection of Q onto the first n coordinates. We now need to make sure that there's nothing else. So let me just write that. Let me just clarify. So this whole thing shows that P is contained, let me just write it in this way, the projection of Q. So now we need to show the other inequality. So let's take any x that does not belong to P. Well, what does it mean for it not to belong to P? It must violate one of the constraints in ax less than b. So if it doesn't belong to P, then there exists some violated constraint. Again, let's just say it's the ith constraint. So say that means that AI. Let me put a hat here so remember we're dealing with a specific. We'll choose any violated, any point that's not in P. There's some I that depends obviously on X hat, so that AI X hat is greater than BI. There has to be some violating constraint. But the fact that U is non-negative, now we're going to use the non-negativity of U. So the fact that U is component-wise non-negative and the requirement that Y is non-negative means that there does not exist a Y such that AI X hat plus UI Y is equal to BI. Because again, AI transpose XI is strictly greater than BI. UI is component-wise non-negative. Y, but by construction, by virtue of this non-negative factorization, Y is by the constraint, by this constraint non-negative. So this can't happen. Okay, so this concludes this portion of the proof. So what have we shown so far? We have shown that that the non-negative rank is an upper bound on the extension complexity. So now we want to show the other side. So now let's suppose, let me write this down so we're crystal clear. So we have shown that the non-negative rank of S is no less than the minimum extension complexity of P. Because we can, given a factorization, we can always build an extension. So now let's show the other side. Now, to show the other inequality, the reverse inequality, to show the reverse inequality, let's suppose that we have an extended formulation. Suppose Q, which is equal to xy, such that bx plus cy is less than d, is an extended formulation. In other words, the projection is exactly equal to P, and it has R inequalities. So is an extended formulation of P with R inequalities. We're going to show that we can use this to find a non-negative factorization of the slack matrix with U and V having no more than R columns, where this is the same R. Okay, so let's see how we're gonna do this. So for each, again, we're gonna look at the vertex. So for each vertex xj, j from 1 to v, these are all the vertices that we wrote down of P. We know that there exists some y, so that xjy is in Q. So let's write out what that is. So let's choose one of them. There are potentially more than one. Let's fix yj such that this pair xj yj belongs to the extended formulation. And now let's let vj equal d minus, this is this d, minus b times xj minus cyj. So I don't want the subscripts to confuse us here. Everything in sight is a vector. D is a vector of size r. And similarly, bxj and cyj are vectors because b and c are matrices. So v is a vector of size r. And the notation is chosen on purpose to suggest what's going to happen. V is going to be the jth row of the matrix V. In other words, the jth column of the matrix V transpose. And also, just by virtue of the fact that xj, yj belong to Q, we know that that this is component-wise non-negative. So not only is it an RR, but Vj is component-wise non-negative. Okay, so now we need to use a few facts from linear programming. So saying that Q is an extended formulation of P, note that this implies that the system Bx plus Cy less than D implies Ax less than B. In other words, for any pair x and y, if Bx plus Cy is less than D, then it must be that Ax is less than B. This is just what this means, and again, this is exactly what we're saying when we say that Q is an extended formulation of P. Now, let me give you an example of this, a picture, so that we can have in mind the geometry of what's about to happen, because we're going to use some machinery from duality that maybe obscures the geometry. Let's look at two inequalities and then a third inequality, which I'll write in a different color. And note that the first two inequalities that I wrote imply the third inequality. In other words, anything in this, let me choose yet another color, anything in this region here that satisfies the first two inequalities clearly satisfies the third. So this is an example where, again, just in 2 dimensions so I can draw it, a system of inequalities implies another inequality. Now, the reason I drew this is that what you can see from this picture is that if I take a convex combination, probably the way I drew it, it looks like if I just take the average. But if I take a convex combination of these inequalities, I can actually form that third inequality. And this simple statement that I said is essentially the statement of strong duality. We know that any non-negative combination of Bx plus Cy less than D is going to be feasible. So we know what's a non-negative combination. So obviously that for any vector p, little p, that's non-negative, if xy satisfy Bx plus Cy less than D, then they satisfy P transpose Bx plus Cy less than P transpose D, because P is non-negative, and so I'm just adding inequalities. The statement of strong duality is essentially telling us that if Bx plus Cy is less than D, then there exists a P such that P transpose Bx plus Cy less than PD is exactly the system Ax less than B. So I'll just write this as informal LP strong duality. Or sometimes this is called Farkas lemma, but this is the intuition, and says that there exists a non-negative P such that P transpose B is equal to A, P transpose C is equal to 0, P transpose D is equal to B. I should have put this is for every individual inequality of AX. So let me write AI. There exists a PI such that PI transpose B is equal to AI, PI transpose C is equal to 0, and PI transpose D is equal to the scalar BI. Okay, so this is LP strong duality, and let's just use this to see. But because we're gonna that's the geometric intuition of what's happening. Okay, so let's see the details here. So let's look at the optimization problem. So let's in particular use LP strong duality to show this precisely, to show that statement. In other words, to show what? To show that there exists, to show that for any I, I'm writing more clearly what I squeeze on the bottom of the page, there exists a vector, PI, that's non-negative, so that P transpose B, C, D equals A0 BI equals, sorry, AI, the ith row, 0 BI. And we're just going to use strong duality. So let's look at the optimization problem. Minimize AI transpose again is the ith row of A, AIX plus 0 transpose Y, subject to BX plus CY less than D. What is the value of this? Well, my claim is that this optimization has value BI. It has to be because this is just saying that there is some feasible X in P that satisfies the constraint AIX less than BI with equality. Clearly, it's not going to be more, and if it were strictly less, it means we could just discard that equality. All inequalities AX less than B have to be, in order for them to be needed, have to be satisfied with equality, but by at least 1 point in the polytope P. Okay, so this is so that's this, and now let's look at the dual of this LP. So the dual is the problem minimize. I'm going to use my variable will be PI. PI transpose the right-hand side here, D, subject to PI transpose the matrix BC equals the matrix AI 0, because that's the from the objective, and also because and I have equality here because X and Y are unconstrained, and I also need PI non-negative because I have an inequality in the primal. So we know that the primal is feasible and bounded, therefore strong duality holds. So by strong duality, the optimal PI star is feasible. In other words, so is feasible. In other words, PI transpose BC equals AI 0. And also the optimal dual, so value is equal to the optimal primal. And so PI transpose D is equal to BI. And that's exactly what we needed to show. Okay, where are we here? What are we trying to do? This PI is going to be exactly my UI in the non-negative factorization. So build matrix U by letting UI equal this vector PI, where in order for each PI, I need to solve this LP to get what it is. Again, we don't care about complexity. We're just talking about existence. So what does that tell us? What is UI times VJ? So this is equal to ui times, let's go back and see what Vj, how did we define Vj? This is how I defined Vj. Vj is d minus b xj minus c yj. And this is therefore equal to ui d is equal to bi. Ui b is equal to ai. And uic is equal to 0. So this is exactly the ij entry of our slack matrix. So in other words, hence, we have a non-negative factorization of the slack matrix, which means that this R of dimension R, and so certainly this R, which was our extension complexity, can't be any smaller than the minimum factorization into non-negative factorization of S, which is also known as the non-negative rank of S. And that is our story. So this shows that the non-negative rank is exactly a characterization of the extension complexity.